let's discuss together population growth. We'll start with a very simple example, and let's see what happens with the population of pennies that can grow if a penny fair doubles the amount of pennies each night. So let's put down the number of nights and the number of pennies that you will have after each night. We need basically to create a graph. You will create first a table. The number of nights is the time that goes by. The number of pennies is the population, let's say, of pennies based on the number of nights that you have. Let me name the nights T and the pennies P of T. So after the first night, you will have a penny. After the second night, you will have 2 pennies. After the third night, you're going to have 4 pennies. The fourth night, the fairy is going to give you 8 pennies because the pennies double. After 5 nights, you will have 16 pennies. So basically what happens is if you look at your T, the P of T, the P of 1 here, is going to be equal to 1. The P of 2 will be equal to 2. The P of 3 will be equal to 4. Or let's say instead of 4, 2 to the second. The P of 4 is going to be equal to 2 to the third, where the 2 right here is nothing else than the number of pennies that you have, the number of nights that have gone through, minus 1. The 3 right here represents the number of nights minus 1. The P of 5 will be equal to 16, that is 2 to the fourth, that is again 2 to the T minus 1. So in general, if you look at the big picture, then the P of T will be nothing else than 2 to the T minus 1. And this gives you the growth, and immediately you can see right here you have an exponential function, because this is an exponential function. And this exponential function depends on the number of nights that have gone by. Let's look now into a more complicated example. In the same way that the pennies are increasing under your pillow, the same way the bacteria increase under ideal conditions, unfortunately. So let's see, we are talking again about population growth here. And what we can say in this case is that the bacteria double every 4 hours. So now you have T again, that it's counted in the number of hours that they pass. And at the same time, we have the population of bacteria, the number of bacteria that grows. And the number of bacteria is going to be represented by some function of T, and basically is going to be how many bacteria you will have. So the information that we have here is that at time 0, so before we start counting the time, the bacteria that you have are 30. So you have 30 bacteria here at time 0. Then after 4 hours, the bacteria double. So the 30 will become 2 times 30. That is going to be 60. And I got this from 2 times 30. Then after another 4 hours, so in 8 hours, The bacteria will double again, so the 60 will become 120. But again, this 120 is nothing else than 2 times 60 of what it was before. But basically, what this is 2 times 230 of what was at 0 time. And if you want to simplify this is 2 to the second times 30. After another 4 hours, and this will be now 12, the bacteria will double again, and you will have 240. That with the same way of thinking is going to be nothing else than 2 to the third times 30. So right here we are increasing 4 hours in every period, as you can see. And here we see how the population increases in those 4 hours. And they increase how? By multiplying the initial population that you have right here, and let's call this P0, times 2 to the third. 2 to the third, the number 3 is nothing else than not the number of hours, but the number of hours that have passed divided by 4. So if you think about the number 12, that is the number of hours that have passed, 12, and you divide this by 4, because in every 4 hours we have a duplication of the bacteria, then this is nothing else than your number 3. So basically I can rewrite this, instead of having 2 to the third, I can write this as 2 to the 12 over 4 times 30, right? And this can be written as 2 to the 12. What is 12? The number of hours, the T, divided by 4 times 30. And what is the 4? The 4 is how long it takes to double the bacteria. So my function, as you can see, P of T, is equal to 30. That is nothing else than my initial population, times 2, and I write it as P0, 2 to the 1/4, let me write it like that, times T, where 1/4 is a parameter. It's a parameter. And I can call this parameter for any type of function that I have. Let's call it R. Right? And this R is determined by the number that tells me how fast the duplication of the population happens, how fast this population increases. So I have 30, that is the P0. I have 1/4, that is 1 over the number of hours that I need to have a double number of bacteria. I have T, that is the number of hours. And what I also have is this number 2. Where this came from, how do I know that this is number 2? Well, these 2 represents nothing else than doubles. Doubles is 2 times, so this is where I find my number 2 here. So for any kind of population growth example or function, we can analyze the situation and we can rewrite the information into a function. And this is what I do right here. Pt is equal to P0 times 2, because it doubles. If it would triple, then I would have 3 here, times R, that is in how many hours it doubles, the fraction that gives me 1 over how many hours it doubles, times T, that is the number of hours. Now, if I want to clean up the function and understand better what is going to happen, especially when I'm talking about doubling time, meaning population that doubles with time, then my function NT, let me call it NT instead of PT, is going to be equal to the initial population of bacteria, of pennies, of birds, of whatever this is, times 2, because it doubles, to T over A, where A is going to be the time that is required for the population to double. And this is something that it would be a good idea to memorize. This function, this formula right here is the formula for the doubling time for the population growth. So let's see an example now where we will be using this formula. So instead of bacteria, we are going to be working with frogs. So we have bullfrogs in a pond. And the graph that we have right here gives us the bullfrog population for the next few years. And it grows exponentially. A few things that we can see in our graph is, again, that the time is on the horizontal axis, right here. So at time 0, at time 1, at time 2, 3, 4, 5 years after the beginning, it will basically tell us how many frogs I have in the pond, and this will appear on this curve right here that I have. So each one of those points will correspond to a T that gives me the number of years that have passed. So right here is the number 2, and Y that is going to be nothing else than the number of frogs that that are in the pond, 225 in this case. So after 2 years I will have 225 frogs in the pond. Also, the initial population of frogs in the pond seems to be 100 here. So the first question is easy to be answered, because the initial population is going to be at the point where the curve crosses the y-axis, where the time is equal to 0. So it's going to be nothing else than 100. Now I want to know how big will be the population after 2 years. So what I need to do is go to the horizontal axis, find the point 2, that is the T. So after exactly 2 years, I'm going to find the point on my curve that gives me 225, and this is the number of the frogs in the pond at that time. So I have 2 points. 2 points are given for this function. The one point is the 0,100, and the other point is 2,225. So what I can do now is that I can find a function, an actual function, that models the bullfrog population after T years in general. Well, what I want you to see is that after 2 years, the population has been more than double. But if you look at the point right here, you can see that somewhere between the year 1 and the year 2, probably after 1.75 years, the population has doubled, has become 200. So observe that, because you have the points where you have on your curve right here, you can visualize the point exactly at the time when it happened that the population doubled from 100 to 200. And this is something important to remember. Now let's go back to the formula that I gave you before that tells me that NT in general is equal to N0 times 2 to the T over A. And this is a formula for doubling, and also a formula that gives us what will be the population after a number of years in a population growth, and in the specific example that we are talking about right here about the bullfrogs. So let me write this formula down here, and what we know is that the NT in general from this formula is going to be equal to N0 times 2 to the T over A. Okay.